Welcome back to Chemistry for Engineers. And this is chapter 3, molecules, moles, and chemical equations. Lots and lots of math in this chapter. So for you engineers, that's a great thing usually. All right. So first of all, let's go ahead and take a look at a few things. Let's just go ahead and talk. And remember, you're filling out your notes template. Um, and that's great. So first of all, we're going to talk about some things. Chemical formulas provide a concise way to show chemical compounds. Hopefully you can see everything on this slide. And an example of a chemical formula is simply, let's say that we're talking, remember that water we know is equal to H2O. And for some things, it's a really big deal to use formulas instead of names because it saves a lot of time. Okay. And then a chemical equation uses chemical formulas to represent a chemical reaction. Okay. And so I'll have an example of that down below. Chemical equations represent the transformation of one or more chemical species into new species. So your reactants, okay, your reactants right here, these are your original or starting materials and are always written on the left side of the equation. And then you have your products, and the products are the newly formed compounds and are written on the right side of the equation. So here I have an equation. Magnesium metal reacts with aqueous hydrochloric acid to produce aqueous magnesium chloride and hydrogen gas. Okay, so let's take a look at what that might look like here. And so first of all, it starts with magnesium metal here. Okay, so that means Mg, and it's a metal or a solid. So we put an S there for solid. And it reacts with aqueous hydrochloric acid. And so that's HCl, aqueous. And you'll be learning more about these. To produce gives you one of these, a yield sign. Aqueous magnesium chloride. So hopefully you remember how to put these together. So we know that that's MgCl2. You should have your ion list and your periodic table. And it says aqueous, so that's AQ. And hydrogen gas. Hydrogen is one of our diatomics. So that needs to be H2. Right? And it's a gas. And then it's always very important to balance this. So you can see here that you have two chlorides. And so I'm going to go ahead and put a 2 here and see if that works. Now that 2, I have 2 hydrogens here, and I have one H2 here, and 1 magnesium here, and 1 magnesium here. So I can go ahead and put 1s here and here and here. And that is a little bit of an introduction to balancing, which will be super important. Okay, and so here's kind of your final equation for this. All right. Now, when we're writing chemical equations, chemical formulas represent reactants and products. And one way to look at this is that your reactants are what you start with. Okay. And products are what you end with. All right. And the phase labels for each of those, a solid is marked as an S, a liquid is marked as L, gas is marked with a G, and aqueous or dissolved in water is an AQ. You'll see me write this with a Q. We'll have a little tail. Okay, so now let's take a look at sodium, at how we would write some of these. Okay, so it says sodium metal plus chlorine gas forms sodium chloride. So sodium is Na, and then again, it's a metal, so it's a solid. Right. And chlorine is one of our diatomics, so it's Cl2, and then we have a gas, and it is going to form NaCl. Okay, and sodium chloride all by itself is table salt, so we know that that's a solid. Okay, and there's no water in here, so we know that it won't be aqueous. And now we're going to balance it, and I can see that in my reactant here, I have Cl2, and in my sodium chloride, I only have the one chlorine there. So I'm going to put a 2 out in front to form 2 chlorines. And then I see that I have 2 sodiums right here. So I'm going to put a 2 right here to balance those. And I can go ahead and put a 1 here just to be very clear. It's understood to be 1 if there isn't one, but I like to put it in just because that can be kind of helpful. We won't forget anything. All right, now the next one that we have down here is copper metal, and copper is Cu, and it's a metal, so it's a solid, plus aqueous silver nitrate. Okay, so again, I am using my ion list, and I know, that silver, just as a review there, is Ag plus, okay, and nitrate is NO3 minus. Okay, so we have silver nitrate, NO3, and it is aqueous and forms gives us a yield sign. Now it says silver metal. So now this needs to be Ag solid and aqueous copper 2 nitrate. So because it's copper 2 nitrate, this needs to be CuNO3 2, and it's aqueous. So we have a little AQ there. And now again, we need to balance this. Okay, so I start here and I notice that I have NO3 2, which means that I'm going to need 2 of these NO3 units. So I'll go ahead and place a 2 right there. Okay, and then I notice, okay, that I have this 2Ag, and so I need 2Ag right here. And now I kind of check through things. I've got 1 copper and 1 copper. So I can put a 1 here and a 1 here to balance that one. Okay. All right, so this is the balanced chemical equation for the combustion of methane. So let's take a look here. Here is your balanced equation right here. So now we're kind of going backwards. Here we have our balanced equation. We have 1 methane unit right here, and that has 1 carbon atom and 4 hydrogen atoms. Okay, and then we have 2 oxygen units here. Okay, and that has our 2 right here, and that gives us these 4 oxygen atoms. And when they recombine, we have 1 CO2 unit right here, which gives us 1 carbon and 4 oxygens. And now you can see here that here's that carbon and here's those oxygens. Okay. And now we have this 2 water units that we're making, and here they are here, 1 and 2. Oh, and then those are 2 of the oxygens here, and then 4 of the carbon. Sorry, 4 hydrogens, and those get balanced just like that. So that's our reaction between methane gas and oxygen gas. Okay. So let's take a look at the law of conservation of matter, also called the law of conservation of mass, and it states that matter cannot be created or destroyed. Okay. So chemical reactions must obey the law of conservation of matter. Okay. And that means that the same number of atoms for each element must occur on both sides of the chemical equation. chemical reactions simply rearrange the atoms present in different molecules. So that's what I've been showing before. And I've been sort of showing you an introduction to that balancing of equations that ends up being just so incredibly important. Okay, so the Haber process is used commercially to create ammonia from nitrogen gas and hydrogen gas. And we're going to write a balanced equation for that. Okay, so let's take a look at what that's going to be. So first of all, we have nitrogen gas, which is N2, and we have hydrogen gas, okay, and it's going to create ammonia. All right. Let's take a look at this. How are we going to do this? Okay, so what we need is we need all the elements on both sides. So there's different ways to do this. I'm showing it in one direction. If that doesn't make sense, then when we're meeting together for our recitation and homework practice, then I can help you out with another one. But see here you have N2. So I'm going to come over here and I'm going to put a 2 in here to show 2 nitrogens. All right. Now, what I can do is I can say, okay, well, now what I see here is I see this 2 with my H3 means I have 6 hydrogens. Now, if I have 6 hydrogens over here, then I need to put a 3 here. So because 3 times 2 is 6. And then I can come over here and place a 1. So now I have a balanced equation for this reaction. Okay, so now let's take a look here. And it wants us to write a balanced chemical equation for the reaction between propane and oxygen. This is burning propane. So we'll start here and we'll say C3H8. And they're not worrying about states in this one. So we'll go ahead and leave that out. Plus oxygen gas. Okay, forms carbon dioxide and water. So let's take a look at where this is going to be. And sometimes the interesting thing here is that you kind of have to go back and forth a little bit. So let's see how this one might work. So first of all, I have 3 carbons here. And so I'm going to go ahead and put a 3 in front of this. Okay. And now the next thing that I'm going to do here is I'm going to say, okay, I have 8 hydrogens here. And with that H2, I'm going to put a 4 here because 4 times 2 is 8. Now what I'm going to do is I'm going to say, okay, so now I have 4 oxygens right here and 3 times 2 or 6 oxygens here. And that means that I have to have 10 oxygen atoms. So if I have to have 10 oxygen atoms here, I'll put a 5 in front of my O2 and I can place a 1 there just for clarity. Okay. Now this one's already written out for us. And so let's take a look at how we can work through this one. Okay, so this may be a little bit trickier because I noticed that I've got a bunch of different things in one place. Okay, so let's take a look here. First of all, let's make a list. I have 3 carbons and I have 8 hydrogens and I have 1 oxygen. Nope. I've got over here. So I have 3 oxygens. Okay. Now let's come over here. And this is just kind of another thing here. Now on this side of the equation, I have 1 carbon and 1, 2, 3 oxygens and 2 hydrogens. Okay. So again, just showing you a little bit of a different way to do this. And so let's take a look at working through a couple things. Okay, so notice here that I have 8 hydrogens, and here I only have 2 hydrogens. So what I'm going to do is I'm going to add in like this. Okay, now I can see that I have 8 hydrogens here and 1, 2, 3, 4, 5, 6, or 6 oxygens. Okay. So, but notice here that I have 3 carbons. So I'm going to add 3 more here. Okay. So now I have 3 carbons, and I have 2, 4, 6, 7, 8, 9, 10 oxygens. Okay, now I notice here, so now what I can kind of do here is I can say, okay, the 3 matches and the 8 matches for the hydrogens, and now I have 1 oxygen here, and I have 2 here. Okay, so that means that let's go ahead and start adding. So I have an O2 and an O2 and an O2. Okay. And so now I have 2, 4, 6, 8, 9. Okay. But I need 10. So I'm going to add half of an O2 here. And that looks kind of interesting. So now look, I have 1 and I have 1, 2, 3, 4. So 4.5 oxygens. You'll see in a minute another way to do this. Okay. And now I have 3 of my CO2s and 4 waters. Okay. So now what I'm going to do is I'm going to multiply through everything. And this is going to become 2 and 9 and 6 and 8. Okay. That's a difficult way to do this, but that's one way to do it. So let's go ahead. I'm going to erase all this, and then I'm going to just show that in a second method. Okay. So now let's take a look at where we're at. So first, what I'm going to do is I'm going to say, okay, I'm going to actually there's this is a very difficult one either way. So I'm just going to show it without all the counting. So I'm going to start by saying, okay, I have C3, so I'll put a 3 here for the carbon. Okay. And then I notice that I have 8 hydrogens here, so I'm going to put a 4 here to account for that. Okay. And I'm going to put a 1 here just so that I don't lose track of it. All right, now on this side, I have 3 times 2, or I have 6 oxygens. And on this place, I have 4 oxygens. And that gives me 10 oxygens. Now, I have 1 oxygen from my propanol here, my C3H7OH. And so I need 9 more oxygens. And I'm going to get 9 oxygens from O2 by putting in a 4.5 or a 4.5. Okay. And so that's when I come through here. And again, you need this in small whole numbers. So this becomes 2 and 9 and 6 and 8. And I can cross those out. Okay. So that's just a second way of looking at one that's quite difficult. Okay. Aqueous solutions. So reactions that occur in water are said to take place in aqueous solution. And just here's a few things here. First, we have a solution. A solution is a homogeneous mixture of 2 or more substances. And just as a little bit of a review here, remember that homogeneous means the same throughout. Okay. And it means that it has visibly indistinguishable parts. So same throughout, you can't see any differences there. The solvent is the part of the solution that does the dissolving, and the solute is the part of the solution that is dissolved. So we have a couple things here. We have compounds can be characterized by their solubility, and we've got some solubility rules coming up here. Soluble compounds dissolve readily in water. Okay. And they're going to be called AQ in solution. Now, insoluble compounds do not dissolve readily in water, and these are going to be solids. Now, we also have marginally or slightly soluble. And this means that a very small amount is soluble. And these are also going to be S or solid in our reactions. Okay, now we have our solubility rules for soluble salt. So let's take a look at what these are, and we'll put in some examples as well. Okay. So first of all, what I've got here is I have everything in green is soluble and everything purple is insoluble. Okay. So first of all, nitrates and acetate salts are soluble. And this is basically just remember that all nitrate and acetate salts are soluble. So anything with an NO3 or a C2H3OH minus is going to be aqueous. All right. Next, we have alkali metal. And alkali metal, we've got lithium, sodium, potassium, remember those, et cetera. So everything in that column one. And the ammonium salts are soluble. So again, those are going to be AQ. And this is another all. Now we have our halogens. Okay. So these here are our, let's see if I can write sideways here. These, my pen's not going to let me write sideways. So these are our halogens right here. Now, chloride, bromide, and iodide, this is an I, iodide salts are soluble, okay, which means that they're going to be aqueous, except with these. So what that means is that, for example, silver chloride, silver bromide, and silver iodide are all going to be insoluble. Okay. And we could also put them with lead 2 or mercury 1. Okay. These are insoluble. They're going to be solids, not aqueous. The really interesting thing here is fluoride. Oh, let's talk about fluoride because fluoride is different. Fluoride ions are generally insoluble. These are going to precipitate out unless they are with the cations from rule 2. Okay. And silver. So that means that silver fluoride or sodium fluoride are going to be aqueous, even though the rest of them are going to be insoluble. All right. So let's take a look here. We have the next one we have is our sulfate. So most sulfate salts are soluble, aqueous, except barium sulfate, lead 2. So remember, this is lead 2, SO4 2 minus, and Pb2 plus, and that's how they. So this one comes together to form PbSO4, and it's going to be solid because it's insoluble. Okay. But other ones, for example, lead 4, which would be PbSO4 2, this one is going to be aqueous because it's not one of our exceptions. All right. Next, we have rule 5, which tells us that most hydroxides are slightly soluble, which means we're going to lump them in with insoluble. And they're going to precipitate out, PPT, precipitate, as well as our marginally soluble ones. These will also precipitate out. The only ones that are fully soluble are sodium hydroxide and, hang on. Sodium hydroxide and potassium hydroxide. Oh, this should be green. Sorry. These are soluble. Okay, so change that should be green in there, the sodium hydroxide and the potassium hydroxide. Okay, and actually, I think, oh, okay, never mind. I'm not going to be able to adjust that just yet, but I will adjust it in just a moment. And then down here we have sulfides. Okay, here, sulfides Carbonates, chromates, and phosphates are only slightly soluble. Again, we lump those in with insoluble because they will form solids and they will precipitate out. Except with the cations from rule 2. So again, we're coming back here to rule 2. If you put any alkali metals with these, then they're going to precipitate out. Okay, let me go ahead and watch. I can change this just like this. No, I cannot. Okay, never mind. I can't change it, but just remember that that it's there. All right, now let's take a look here at these equations, and they want to know which of the following compounds are soluble at room temperature. So the first thing that you need to do is you need to go to your ion list. Okay, and you need to make these compounds. So here we have our potassium and chlorate, ClO3 minus. Okay, so these come together to form KClO3. And up above, if you look at rule 2, which talks about every time we have a potassium, we can see that this will be soluble. So we can put a little AQ here after it. Now we have our calcium chloride, and again from our ion list, that's Ca2 plus and Cl minus, which forms CaCl2. And if you look at rule number 3 above that talks about your halogens, you will see that this one is going to be soluble, and so we can also put a little AQ after that. Now have barium sulfate. So barium is our Ba2 plus, and sulfate is our SO4 2 minus. So these balance together to form BaSO4. And if we look at rule number 4, we can see sulfates are usually soluble, except with barium. Barium is one of our exceptions. So this is going to be insoluble. And we can put a little S after it for solid. Now we have our potassium permanganate. So we have our K plus, and then our permanganate, which is MnO4 minus. And when these come together, then we have K MnO4. And if we look at rule 2, that talks about alkali metals, we can see that potassium is going to always be soluble. So this is going to be soluble, and we can put a little AQ after it. And then we have our silver nitrate, which is going to be Ag plus with an NO3 minus. Now, there aren't many silver compounds that are soluble in water, but you notice with our AgNO3 that we have a nitrate. So our rule number 1 tells us that nitrates are always soluble. So this is going to be a soluble compound, and it is we can mark it as an AQ. Now, last but not least, we have lead 2, Pb2 plus, and phosphate, PO4 3 minus. Okay, so when we bring those together, we have Pb3, PO4 2. And if we look at rule number 6, we see that while that phosphates tend to be only slightly soluble, except for a few exceptions, and lead 2 is definitely not one of those. So this is going to be insoluble, and we could put a little S after it, indicating that it is going to be solid. All right, now let's take a look at a few things. We have our electrolytes, and electrolytes are soluble compounds that conduct electricity when dissolved in water. So they have to conduct electricity, and that means that they have to have ions in them. And we will do a conductivity lab that's going to be really great with this. In fact, you've probably already done this conductivity lab. And again, when dissolved in water. So we have to be able to dissolve them in water. Electrolytes dissolve with just a dissolve dissolve or dissociate partially into ions. So when we're talking about this, we're seeing only a partial solubility here. Okay, so an example of a weak electrolyte, maybe, and I have some different actually I think I have some examples of this a little farther on. Um, but a weak electrolyte might be an example of, say, calcium hydroxide, because remember that calcium hydroxide is only marginally soluble or slightly soluble, which means that in the presence of water, you're going to, most of it is going to stay solid. And then you'll get a tiny amount that forms calcium ions and hydroxide ions. Okay. Now, strong electrolytes are going to be different. Strong electrolytes dissociate completely. So, an example of a strong electrolyte might be potassium nitrate. And if we start with solid potassium nitrate and put it into water, we're going to get complete dissociation, K plus and NO3 minus. It all dissociates like this. And that's a strong electrolyte that falls apart completely. Non-electrolytes are substances whose solutions do not conduct electricity. They have no ions in solution. And what you're looking for here is you are looking for covalent compounds. Okay, because covalent compounds do not have any ions. All right, so now let's look again at our non-electrolytes. Non-electrolytes are covalently bonded materials. Many of them do dissolve in water. For example, sugar. This is glucose. They dissolve in water, but the molecules remain intact, and so they do not conduct electricity. And so the water molecules aren't shown explicitly, but interestingly enough, you can write an H2O over it just like this. And what this means is that you're being dissolved in water. And I will usually do that. Usually put a little water over it to just be very specific that I'm doing a solvation here. Now let's take a look at some electrolytes specifically. A dissociation reaction, this is just another dissociation reaction, occurs when ionic solids dissolve in water and break into their constituent ions, which conduct electricity. So I actually showed this in a previous one, but what we're showing here, and again, you could also write H2O over this to be very specific that that is what you're doing. You're doing a dissolving type of reaction or a solvation. Okay. Now let's take a look at a couple things. Here's some chemical equations, and we're going to be talking about some very specific types of chemical equations. First of all, we will have a molecular equation, and in a molecular equation, we show everything as compounds, okay, plus the state. So here is a molecular equation between nitric acid and ammonia to produce ammonium nitrate. Okay, so this would be, again, your molecular equation. All right, and do is we can show a couple more here. And that's the complete ionic equation and the net ionic equation. So in the complete ionic equation, what we've done here is we've broken this up. So remember that this was HNO3 aqueous. Okay. And so we've taken this aqueous and we've broken it up to show that it's not actually HNO3 in solution. You have H plus ions and NO3 minus ions. Now, because this is a gas, it stays together. We're only breaking up our aqueous solutions. And then over here, remember that in the previous molecular equation, we had NH4NO3 aqueous. And so because it's aqueous, we've broken this one up as well. Now, notice in this complete ionic equation here that you have this nitrate and it doesn't change. It's as an ion on both sides. So what it's called is a spectator ion. So the net ionic equation is only looking at the things that are reacting. And so this is an equation that shows H plus and ammonia forming the ammonium ion. All right. Now, acids and bases. So, acids are proton donors or substances that dissolve in water to produce H plus or H3O plus. Okay. And some examples of that are first of all, here we have hydrochloric acid, and hydrochloric acid forms H plus and Cl minus. Okay. And each NO3 forms H plus and NO3 minus. And H3PO4 forms 3H plus and PO4 3 minus when it's dissolved in water. Okay. Next, we have bases, and bases produce OH minus in water. Now, not all bases have OH minus in them. A lot of them, for example, ammonia doesn't have a hydroxide, but it does produce OH minus in water. So I'll show you that as well. First of all, our sodium hydroxide here in water would form Na plus and OH minus. And this one is complete because it's fully soluble. Now, calcium hydroxide is only marginally soluble. So you can actually write one of these. Okay. So you'll notice that it goes in both directions, indicating that it doesn't go to completion. But that would be Ca2 plus and 2OH minus. So before in the previous one, I showed that only some of it dissolved, and now I'm showing it with a double arrow. Now, another one here that we could work with is ammonia. So ammonia is a base, and when it comes into contact with water, okay, so we've got our ammonia and our water. So now we actually have to kind of show the whole thing here. What we end up with is we end up producing an oh, hang on. The 4 goes down below. Okay, we have NH4 plus and OH minus aqueous. And again, it's not a very strong base, so we'll draw a double arrow here. And what you have is because your water is HOH like this, and one of these hydrogens is going to go on the ammonia, and the other OH minus is kind of left behind as that OH minus. And that's how something that doesn't have hydroxide in it produces hydroxide in water. Okay. Now we have we have a page here that lists some strong acids. And we can see the dissociation here of a strong acid, HCl plus H2O forms H3O plus and Cl minus. That's just another way of writing it with that H3O plus ions where you actually show the water as part of it. And then we show the solution of sodium hydroxide to form Na plus and OH minus. And this is a nice list of strong acids and bases. You can go ahead and write all these in. Okay. And then we have some weak acids and bases that dissociate partially in water. This is one way of writing our acetic acid, but the way that we're using, because it shows our functional group just a little differently, is HC2H3O2. And then this is C2H3O2 minus. Okay, so this is acetic acid, and this is the acetate ion. And here you can see those double arrows showing that we have only a partial dissociation. And these are just giving you some examples. It's not a total and complete list of by any means. Both of these lists are only partial. All right, we're going to and pause there, and we will come back later for some more chemistry in part 2.